Hi, in this video we are going to continue looking at our representation of floats. So the first thing we can do is look at the help, if we want, for float. So we can use the help command, and you can see that the float has a single constructor that takes some parameter x, and it will try to convert a string or number to a floating point number if possible. So this means we can do something like float 10. We can take an integer and we can make a float out of it. As you can see, we get 10.0. Of course, we can also use a floating point number already, so that will work too. It's kind of superfluous, but we can do it. We can also use strings that can be evaluated as numbers. So let's say 12.5. That will come back as the float 12.5. Now, you remember with dealing with fractions, we could do something like 22/7. Well, that's not going to work here, right? We are going to get this value error. It could not convert it. If you really want to be able to do that, you're going to have to first create a fraction and then cast it as a float. So we can do it this way, right? So we can import fractions, and actually, let me do this. From fractions, import fraction. We're just going to import the fraction class itself. We don't need the other ones. So here we might say a equals fraction of 22/7. And now we can say float of a. We can take a fraction and convert that to a float. That's perfectly fine. Okay. So the next thing I want to point out very quickly is this whole problem that we have with the internal representations being infinite. And we can take a look at something like, 0.1. Well, if we print 0.1, it looks just fine. It's like, well, what's the problem? It's 0.1. Well, the problem is that Python is kind of, fooling us here with the display. When we're printing 0.1, it's kind of, formatting it to a smaller number of digits, a smaller precision, if you want to think of it that way. But in fact, behind the scenes, that number is not 0.1. And we can do something like this to show it. So maybe we think, well, I'm not sure that 0.1 is exact. What if I decide to show, maybe 15 decimal points? Like, well, that still looks pretty good, right? Even with, 15 digits after the decimal point, we still have a 0.1. It looks like it is exact. So let's push that out a little bit more. And let's go to 25. And now you can see that we do not have exactly 0.1. It's slightly off. All right. And of course, now if we use something that can be represented exactly, and remember that we looked at 0.125, right? And we saw that we can represent 0.125 as an exact value, right? Because what is 1 divided by 8? It's 0.125. So 1/8, that's 1/2 to the power of 3, which is basically, part of that expansion, that representation that we had using powers of 2. So if we format 0.125 and we go to 25 digits after the decimal point, you'll see that it is exact. So we have 0.125 and everything else after that are zeros. So just something we have to watch out for. And why do we have to watch out for that? Well, I'll give you a little preview of what we're going to look at in the next video. Let's say we define a to be 0.1 plus 0.1 plus 0.1. And then we define b to be equal to 0.3. Now we test the equality. Is a equal to b? And the answer to that is no, they're not equal to each other. Why? Well, again, let's just look at format of a with 25 digits. This is what we get. And let's format b with 25 digits after the decimal point. And as you can see, they're not exactly equal. And that's because we have these approximate representations for our floating point numbers. Even though they have an exact representation in base 10, 0.3 is exact in base 10, 0.1 is exact in base 10. They are, however, not exact when you use base 2 representations. All right, thanks for watching, and I'll see you in the next video.